Okay, so our next goal is to use another IoT very popular IoT technology and design a localization algorithm. Okay. In other words, we are trying to see if we can use RFID systems for localization. So, when you talk about this, you talk about several items which are tagged, and then there is a reader which is able to read off the tag ID. Okay, right. It is a very simple system, and you see the good thing about this RFID is there is a large number of tags which do not need any battery power, although you can also have BAP tags. You can have battery assisted passive tags, that is they will respond only in the event there is a reader, but they can assist, they are assisted by a battery, which means range can improve, vastly it can improve, but that is one special case, do not worry about it. Just take the case of totally passive tags. And in the previous course we spoke so much about those tags, the protocol of RFID, the different type of tags that are there, different applications for RFID, so on and so forth. It is good for you to go and refresh that before you start looking up anything related to RFID here, because I am just going to get into localization directly. Okay. Now, when you say localization of tag, why do you need it first of all, and what are the scenarios? Thing is, you can have a scenario where you take the case of a factory environment. Okay. It is a production place and there is an assembly going on of a certain part, let us say a large part, let us say an assembly of an aeroplane, just as an example. Okay. You are trying to put together the fuselage, the different components of the aeroplane, the wings are getting assembled and different parts are coming together and sort of being towards the final goal, you are trying to get the aeroplane out. So, there are parts coming from subsystems and subparts coming from different parts of the factory, okay, and then because they are manufactured at different places, perhaps within the factory or also sometimes away from the factory some other place, and they are coming in. So, what is typical? Typical is that there are multiple cartons on a vehicle and there are readers at some point, and the readers are essentially pointing towards a door, for instance. It could be the entrance to the place where integration is happening, and tags are being read. Okay. As the cartons are moving across, the tags are moving, right. In other words, if the carton is moving, the carton has many tags, many small subsections are there, and your issue is that they are all packaged in one. Okay. And readers are placed in one place, the vehicle is moving across with which carrying those cartons. This is the, you can imagine that, have such an imagination. Now, issue is, just imagine the tags are moving, if the carton is moving, the tags are moving, and this reader has to identify read tags, which is quite okay, that is not a problem. But now, if you are asked the question, where in that large carton is a particular subsystem that you want to pull out, okay, right, then or even imagine that within that subsystem directly has to get integrated into the major system. You want to know whether all parts of that subsystem are localized, they are all available, they are all placed, and you want to know the location of each one of them. Okay, both possibilities exist. So, in other words, at a high level, let us assume you are interested in localizing the parts, subparts, subcomponents, component level localization of that large carton which is likely to be part of a major system. Then you need a localization algorithm, right. Now, if you go back and look at the previous lectures and all that, you realize that RSSI is a good indicator which tells you that you can do some sort of ranging with it. Let me show you a small picture of such a system. Look at this picture here. The x axis has distance and the y axis is the received signal strength indicator, which is a nice indicator available at the reader which says how far is the tag, right. For instance, you can say if the RSSI is high that you read, then you sort of know how far the tag is from the reader, and you could essentially keep marking them and then try and find out how. So, you can actually map somehow, although this is not a linear relation, somehow you should be able to establish some sort of a relationship between RSSI and distance. However, this picture works only if it is under very ideal conditions. And what are those ideal conditions? You should have line of sight, okay, and you should ensure that there are no reflections. The reflections component of reflections is minimal, reflections are minimal, in fact 0, close to 0. There is also one problem which with this graph, I can tell you this, that whatever you do in terms of estimation of distance to RSSI, all your distance RSSI measurement reliability, high reliability is achieved only up to some distance, okay, from minus 40 to let us say up to about minus 55, okay. At best about 15 dB is all that you have which actually works. This I will say is 55, okay, just for argument's sake I am just giving you some things for you to make a note. So, your reliability, your ability to read accurately is not very high. After this you really do not know whether your minus 60 that you read is really mapped to a certain distance, or is it coming because of any other condition, maybe due to reflections or lack of line of sight and so on, okay. So, this is the problem. So, RSSI, while it is useful to plot something like distance versus x axis distance and y axis RSSI, it is not so useful from a practical perspective, because the range prediction that you can do or the distance prediction you can do is over a very small fall in signal strength. Beyond that would almost be impossible. You may now ask the following question, that in the example that we are talking about, the carton is just passing by and then there is a reader here, where is the question of not having line of sight. But imagine that is a very ideal way of imagining, right, because there can be lot of people, lot of other kind of traffic that is coming in between the reader and the carton for sure, and also the range. You can't have readers wherever you wish in a manner you make the technology suitable for making a measurement. That is not the way. A factory floor has certain rules, certain areas which are marked as dangerous, and there are safe areas where you can place things, and there is a protocol, there is a rule by which vehicles move there. From a safety perspective, there is a safety officer in every production floor who is just observing what are the kind of violations that people are doing, and if it crosses a certain threshold will have to take action, because it costs a lot of money to companies if there is a worker who has got into an accident situation due to certain oversight of certain safety measures. So, therefore, you cannot place the antenna wherever you like. There are positions in the factory floor where you can place such antennas. This may actually stress the whole system, that typically RFID tags to readers is something in the range of 20, not exceeding 20-22 feet, which is roughly I would say hard to quantify, but you can have a ballpark anywhere between 5 and 7 meters. It will work very well, and beyond that is difficult. So, you are already stressed out in terms of this picture, that this 5-7 meters is essentially might actually fall here, okay. So, now you arrive at a situation where RSSI is almost impossible to be used, okay, because if it is mapping here, let us say this is all your 1 meter business, okay. This is between 1 to 2 meters, okay. Beyond this is all more than 2 meters, okay. If it is greater than 2 meters, then you obviously have a problem that this picture cannot be used anymore, and this is reality. This is reality. Even if you have readers facing the tags in the on the factory floor, because you are at such a distance, there is no way by which you can actually predict the distance of a particular component, because ranging is the first step in towards localization. So, ranging with this kind of RSSI signature is not going to work. Fine. Having motivated ourselves into the RSSI part, that it is not a good indicator of ranging of distance, physical distance, what is the other signature that you can get from a signal, right? It is clear, if you take a sine wave, one is the amplitude. In a way this is amplitude, right, this is power, it is more like power. RSSI is received signal strength indicator is actually power of the signal. If you look back at the basics of any signal, one is power of the signal, the other is the phase of the signal. Phase can be a good indicator. RFID related localization, by and large, any paper that you take, any literature survey that you do, essentially looks at phase based approaches towards localization. Now let us see what are those algorithms, what are those techniques, before even getting into algorithms, what are those techniques that are that can be used for the purposes of phase based localization of RFID tags. That is the first part. Second part is, you cannot imagine that all scenarios with respect to localization fall under the paradigm of a fixed reader or multiple readers and a carton that is cutting across, that is moving across, getting into the factory floor. That is one scenario. The second scenario is, there are objects inside a warehouse, it could be garments, it could be kitchen items, it could be any big departmental store, right, having kitchen items and so many other related things, which are all placed on racks, and then there is a reader that moves, okay, trying to localize. So, both possible scenarios will have to be taken into account. One is tag moving and the other is the reader moving. So, it could be one reader or it could be multiple readers. Let us start with some very simple situations. Even before getting into any demonstrations, we must know a little more about phase based localization and understand what are the different types of phase based localizations that are involved, and after that narrow down to one of them and then try and show a demonstration of that essential approach, which will sort of summarize the phase based localization. You may have to come up with novel algorithms if you have to use the phase signature in a very effective manner. So, with this in mind, let me now draw your attention to a paper which I read recently along with my two project staff, Tejaswini and Sanmay Patel, who helped to understand and mark out areas in this paper which essentially talk about RFID localization. Look at the title, it says we are looking at UHF RFID tags. Again, I do not want to get into the detail because you should look at the previous course which talks about UHF RFID tags. These are all the sub 1 gigahertz tags. We are also talking only about passive tags which do not have any battery associated with it, and just that there is a reader that is throwing power on the tags. If you look at this paper is interesting because it talks about some very basic stuff. We describe three main techniques based on PDOA, phase difference of arrival. Okay. So, what are the three ways? One is time domain, the other is frequency domain, and the third one is the spatial domain. Let us jump into and look up directly what we mean by the PDOA, TD PDOA, FD PDOA and SD PDOA. Okay. This will sort of clarify the basics. So, let us jump to that part. Let us look at TD PDOA, which is the time domain phase difference of arrival. It is all written here very well. Okay, let us see. So, first look at this picture. Picture says the reader is fixed to a position, is fixed to one position, typical of what I mentioned about the factory floor, and then there is a carton and the carton is carrying a number of tagged components, and you are interested in localizing these tags. So, the tag is moving across, and then so let us see what exactly you have to do now. The idea is that you have to estimate the projection of the tag velocity vector, this is that v, on the line of sight between the tag and the reader by measuring the tag phases at different time moments. You are measuring phi 1 at this instant and phi 2 at a slightly later instant, okay, because the tag has moved to some other distance, is moving along. So, you will get another this one, right, a tag reading, measuring the tag phases at different time moments with so you are assuming that this tag is moving at a constant speed some distance away from the reader. Now, the idea is if by measuring the phase of the tag signal at two different time moments, you are taking the derivative of the phase with respect to time, which is essentially giving you the velocity projection, right. So, you can see that Vr is equal to minus c time divided by 4 pi f dou phi by dou t. Basic principle of trying to estimate the velocity of the tag with using these phase signals that you measure at two different time intervals. This is essentially the core idea of TD PDOA. Now, let us look at FD PDOA, which is essentially the frequency domain phase difference of arrival. Any time you read such paragraphs, you have to keep imagining what are the assumptions under which such a measurement is done. This is absolutely critical in such a course. Okay. What are the assumptions? What are the underlying assumptions? Look back at TD PDOA, look at the assumptions that it has made. Now, let us see what is the assumption here and how do you do a measurement. It is not a setting where the reader is fixed and the tags are moving, it does not make that assumption. It is trying to do a localization using another technique for some other scenario. So, let us look at here. It allows the estimate of distance to the tag by measuring phase tag phase at different frequencies, which means again you have to go back to your fundamentals. What can this reader sweep across? What are the sweep frequencies that the reader can provide support on? And by the way, this technique is also something that FMCW radars, which are very popular in automotive applications, actually use, and this paper is actually trying to make a parallel to that. So, the technique is quite simple. You measure the phase of the tag signal at several frequencies, 2 or more frequencies, taking the derivative of the phase with respect to frequency and assuming that other two components of the tag phase, that is phase offset and tag phase tag backscatter phase, do not change with frequency or can be removed, nothing but calibrated out, and the tag has not moved much. This is important. During the measurement we can calculate using this very simple expression again, which is given here, right. Okay. Now, he says if you look at this, note that using several different reader antennas and applying FD PDOA to each one of them, one can localize the tag in 3 dimensions like it is done in FMCW radars. This makes one critical assumption, I will just like leave it there. You have a large sweep bandwidth, okay, only then this is a good technique for you to try. Now, that brings us to the third way of localizing, which is based on the spatial domain phase difference of arrival. Again, moment you see such a picture, you have to look at it and say what are the assumptions under which this technique can be applied. Now let us see, you have reader with multiple receive antennas. You can see there is RX1 and RX2, they have a separation. What should be this separation? You have to ask yourself, is there a limitation on this? How should I set A in this small a, how do I set this? And you see there is a transmit antenna which is throwing power on the tag, and these two receive antennas are reading off the tag response. Of course RSSI will be there, but we do not use it, but we are interested in the phase information that the readers antenna actually, the antennas actually read off. One is phi 1 and the other is phi 2. Now it is quite simple, if you have a separation of A between this RX1 and RX2, D1 is the distance between the tag and RX1, and D2 is essentially the distance between RX2 and the tag. It is now simple that if you take by measuring the phase difference phi 2 minus phi 1 of the received tag signal at two different receiving antennas and attributing it to the path difference D2 minus D1, right, we can approximately calculate 2-dimensional tag bearing. You can find out using arc sign of this expression. Now essentially this brings us to a very important point, which is A, right. How is this A to be used? A is the spacing between the two receiving antennas, and it has certain ways by which you can set. Okay. The transmitted antenna can be located anywhere, that is not important, but phase measurements on antenna 1 and antenna 2 can be done simultaneously. This is a very simple technique where you are essentially trying to convert the phase difference into path difference. This is the crux of the story, okay. And then this simple expression you can actually calculate theta by just measuring phi 2 and phi 1 and knowing A, it is quite simple that you can actually calculate theta, okay. Rather theta can be approximated to this by using arc sign of this expression. Now we spoke about this receive antenna separation, right, and we also looked at that A, which is essentially the receiver antenna separation. Now question is, how should you set this A, right? There is a full paper theory on how this should actually be set. It is quite intuitive actually, okay. Let me show you some pictures on setting of this A and how you will trade off, okay, with ambiguity. You will trade off ambiguity with resolution. This trade off you have to understand very clearly, okay. So let me point you to this. Supposing you have A, the separation between the two antennas set to lambda by 2, okay. You know the frequency of operation of RFID, from there you find out lambda and then you do lambda by 2, okay. Supposing you have lambda by 2, just look at this picture. There are two antenna, you can see these two dots here, there are two antenna. Similarly, if you have lambda separation, you have two beams going out this way. Supposing you had 8 lambda separation, right, this is A, please note, again I am coming back and connecting it to A. Supposing you have 8 lambda separation in A, and what if you had a separation like this, which is essentially the white beam in figure 3A, this is A, acts as a filter on figure 3C on this, as a filter on figure 3C, removing ambiguity while maintaining high resolution. So if you have an antenna which is sort of hybridized, separation which is hybridized, you would get something like figure 4. Okay. Now you must understand this picture and keep the following in mind. The takeaway indeed is, it is nothing but the trade off between improving resolution and removing ambiguity. As the separation of the antenna pair increases, the number of beams also increases, that is obvious, causing ambiguity in localizing the source, which is marked in blue, which is nothing but the tag of interest. On the other hand, each beam gets narrower, leading to higher resolution. Right side 8 lambda, if you do, the resolution is very high, ambiguity is extremely it is very highly ambiguous. In other words, the resolution is good, but ambiguity is also very high, very high ambiguity. You do not know in which one of these beams essentially the source is cutting. So, it is almost difficult for you to find out. If you do lambda separation, you see out here a lambda separation of between the two antenna, then you have two receive antenna. Please note again, because I want you to go back to the picture that I showed you. You have this problem that one beam is going in a different direction, and the other beam is actually holding on to the tag. So, you have a lot of problem there as well, and although the ambiguity is just down to either it is in this beam or in that beam, right. So, it is essentially that. But if you take the lambda by 2 separation, the resolution is poor. The resolution, you do not know where in that beam the tag is actually located, but ambiguity is not there, it is almost eliminated, you know for sure it is there. So, you can see that the ambiguity really is down. So, essentially we are trying to trade the ambiguity to resolution by having different separations between the antenna. All of this is captured in this beautiful paper which is called RF iDraw. This paper was published in one of the SIPCOM conferences, and I think I encourage you to essentially read this paper in great detail, so that you will appreciate the evaluation done in this paper. So, this paper essentially is a realization of different principle of leveraging multiple antenna and how it can improve both tracing as well as localization accuracy. It uses state of art positioning systems, and all of them slowly you get trapped into a situation where you need an array of antenna array, because you will be able to do SD PDOA provided you have multiple receiving antenna. So, everything is moving in that direction, right. And so, if you have to obtain a high accuracy, you need to have a narrow beam, and therefore, you need large number of antenna, and separation we discussed separately. I mentioned to you already how the separation should be. So, I will not repeat that part. Okay. So, then let us go slowly into this picture which you are perhaps already familiar with, the SD PDOA, which is again back here. What is this picture saying? There is a tag which is S. In this paper they use S as a notation, and there are two positions for the receiver antenna. One position is this I and the other position is J, and they are separated by a distance D, right. You in the other discussion we looked at the two phases which are red, which was called phi 1 and phi 2. Here he has converted that into distance, also there was distance there. So, this DSI and DSJ are essentially distances from the source to point I, and DSJ is from the distance between the source to the point J. The distance DSI is greater than DSJ by this amount, which is essentially delta D, which can be easily computed from this separation distance capital D and cos of that the angle theta here, and that is essentially this paper. This paper is essentially looking at the underlying assumption of underlying computation of angle of arrival using the rotation of RF signal by 2 pi for every lambda distance. This is not hard for you to imagine. If you take a picture like this, supposing I take a new sheet, let me take a new sheet to explain this. If you take a sine wave like this, what should this be? This should be lambda, right, this is lambda. So, this is 2 pi, right, this is nothing but 2 pi. So, it is not hard for you to imagine that this is indeed lambda. So, let us go back and connect back to this picture here. It says you can look up this part here, the phase of an RF signal rotates by 2 pi for every lambda distance, where lambda is the wavelength. Specifically, let us consider a signal source at position S and a pair of receive antennas I and J. I spoke to you about that already. You have phi I and phi j should lie between 0 and 2 pi, right. The distances and the received phase signal phases have the following known relationships due to phase rotation. You can estimate, you can calculate phi I this way and phi j in this way, both are identical as you can see, except that this is dsi and this is dsj, and then you find out the phase difference phi j minus phi I and relate it to the path difference between the two signals, and essentially you come up with this expression d cos theta by lambda is equal to the phase difference between j and I positions of the antenna with some constant k here. Okay. So, essentially this is what the paper essentially is looking at. We would use this phase difference, convert it to path difference and construct what are known as multiple hyperbola and look at the intersection of these hyperbolas and to determine the exact position of the tag.